Morning, everyone. Thank you for watching the video. Apparently, we cannot have class next week, and yet we need to cover more of the pressure vessel combined loading. So I'm making this video. Hope you like it. All right, let's start with the pressure vessel. So we have talked about the pressure vessel last time, right? So what simply you can see is that we're gonna have a shape like this, okay? And this will be the cut. And what we're trying to do is we're trying to find the stresses in this vessel. Now, on this surface of the vessel here, I can put a strain gauge this way, strain gauge that way, and I call it sigma L, which means longitudinal stress, and sigma theta is a hoop stress, right? These are the two-dimensional stress we're going to have. And from last lecture, we mentioned that all this can be expressed by the internal pressure of the vessel, here P, and the diameter or radius of the pressure vessel, that is R, and also the thickness of the vessel, that is T here. So to say this, sigma L, which is longitudinal stress, equal to pressure multiplied by the area, which means is this cut right here, so it's pi R squared, divided by the 2 pi r, which is the circle here with the thickness t. So 2 pi r multiplied by t. So r canceled, and then I have pi canceled as well, pr over 2t. Okay, and consequently, if I do a theta, that is a hoop stress, right? And the hoop stress gives me a area like I drew it last time. Should be the shaded area where I have a stress is the hoop direction, theta, 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 theta. And also, let me change the color right here. I have the pressure going to negative away of P here, P, P. Okay, so after I do that, I have a equilibrium. So I have P means pressure, and this length here is L, multiplied by 2R, L, let me switch the thickness here to thinner, and divided by a strip. Here has a thickness T, so T multiplied by L multiplied by 2. Okay, so now I got L cancel, 2 cancel, I have PR over T. All right, so these are the longitudinal stress and the hoop stress theta. Okay, so now I have the two stress components on the surface of the vessel, but don't forget, this is on the outside surface of the vessel. So if I want to draw the strain gauge setting, so I'm going to draw the strain gauge in red, this will be the stress state I'm looking at. It is on the outside surface of the circle right here. Okay, so on the outside surface of the circle right here. However, though, if I put a strain gauge inside of this vessel here, inside of this vessel here, I have to consider the pressure generated inside. Okay, so I have to say here, this is the outside, okay, or exterior, and I have to move on to interior or inside, interior stress. For the interior stress, I naturally will still have these two components, so I'll have sigma L equal to a PR over 2T, sigma theta equal to a PR over T, but I have to consider sigma R now, since this is radial stress direction, has a negative P. Okay, why it is a negative P? Because this is tension, and this is also tension, and that is compression. All right, so now you realize I have two different stress states. Okay, because on outside I don't have any stress exerted on the surface, but from the inside I do have a pressure that is P right here exerted on the inside point. Exerted on the inside point. Okay, so this is the stress, right? This is the stress in the pressure vessel. All right, now let's take a look at the example how we can calculate the stress component in the pressure vessel in the practical application. Okay, so here's one example. All right, so I'm going to draw the pressure vessel like this, as you've seen from the previous drawings, and now I'm going to place string gauges. I'm going to place string gauges on top of it. Okay, and before I do that, let me label the axis. So I have this is so-called x axis. This is so-called y axis. Okay, and my string gauge is going to be a very weird pattern. I'm going to have one string gauge going this way, the other string gauge going this way, and the third string gauge going this way. All right, it's a very strange setting. And now to make it more apparent, I'm going to zoom in. In this region, okay, and show you the detailed strain gauge distribution. So if I zoom in, I'm going to show you the strain gauge goes this way. Okay, on the side, bottom this way, horizontally, and the other way, symmetric, like that. Okay, and the orientation of it follow this triangle right here. And now this is 60 degree. 60 degree, okay? So needless to say, if I set my XY like this, my theta for these three string gauges, let's name them A, B, and C, okay? It's quite apparent, so I can say theta A would equal to what? 0, is that right? And theta B would equal to this fellow right here. So it's 180 minus 60 gives me 120 degree. All right. And now theta C, be careful now. Theta C depends on how you look at it. So the way I look at it right now is going this way. So let me label it out. Okay, so my theta angle right here for C is right here. Okay, so I use the red color here to be different from the other. So theta C here right now is actually 60 degree. 60 degree. All right, so this is my strain gauge setting. Okay, so the question or the problem is actually this. We have a setting like this, a free surface of steel, okay? And we have a strain rosette on the surface of it. And we say if we know the strain settings or strain readings, epsilon A equal to 130 micrometer per meter, okay? That is essentially equal to 133 microstrain. Epsilon B equal to a minus 92 microstrain. Epsilon C equal to a minus 319 microstrain. Okay, so the question is, okay, if I want to find out the stresses on the surface, and I ask you, I want to find a particular orientation. Given that the theta n here, shown in the drawing, is equal to 50 degree. Okay, these are the input. Okay, these are the input. I'm going to ask you, what is the stress in terms of sigma n, sigma t, and tau nt? Tau nt. Okay, so these will be the output. Okay, these will be the output. So how to do it? How to do it? All right. So this is of course question number 1. All right, question number 1. This is output. Okay, so how to do it? And now I have all the strain readings. I have all the geometries on the strain rosette, and I'm trying to find stresses. So I need to ask myself what kind of properties I need to convert from strain to stresses. So of course, right? Of course, the modulus have to be given, and the Poisson ratio has to be given too. Okay, so now I have both the input and I'm going to find the output. So first thing first, right? So solve it. First thing first. Step number 1 is I need to find out the string transformation. Isn't it? So I need to find out how can I transform the strain from XYZ to the strain in ABC, or vice versa. So I'm going to use that equation as I shown before, epsilon n equal to epsilon x cosine squared theta plus epsilon y sine squared theta plus a gamma xy sine theta cosine theta. Okay, we're going to use this transformation equation to convert the strains in different orientations. All right, so now how are we going to use it? We're going to use it in this way because, okay, let me flip the size, because we know theta A equal to 0 degree. So we have strain A, which is 130 micron strain, will equal to epsilon x cosine squared theta, which is 0, plus a epsilon y sine squared theta, 0, plus gamma xy sine theta cosine theta. Okay, which also 0, sorry, here, let me take this one out, my mistake, apologize, sine 0 and cosine 0. All right, so of course this is gone, 0, this is also gone, 0, and this is 1. So I essentially have epsilon A equal to epsilon x. Okay, this is for strain gauge A. Now strain gauge B, theta B equal to 120 degrees. In case you miss it, let's take a look, right? Theta B, you see here, 120 degrees, right? We have that. And now, with that, I can write another equation, which is epsilon B equal to a minus 92 equal to epsilon n cosine 120 squared plus epsilon, sorry, this is x, epsilon y sine square 120 and plus gamma xy sine 120 cosine 120. Okay, and be careful now, we don't really know gamma xy, so this term has to stay here. So let's rewrite quickly, okay? Now I have theta b gives me this equation. Now, when I come down to theta c, where theta c equal to 60 degrees. All right. Now the third equation will read as epsilon phi equal to minus 319 microstrain equal to epsilon x cosine theta phi, which is 60 degrees, so 60 degrees squared, plus epsilon y sine 60 degree squared, plus gamma xy sine 60 and cosine 60. And that is for my theta theta c, right? That's for my theta c. Okay, so I want to list all these equations down. Okay, all these equations down, but I want to list in a certain format. So this is what I'm going to do. I'm going to use a matrix. Okay, how am I going to use the matrix? I'm going to use these ones. Circle as red as unknown. Okay, and I'm going to add this one as 0 multiply epsilon y plus 0 up multiply gamma xy. Okay, so now here's unknown, unknown, unknown. Okay, all right, so here we go, right? We have 3 unknowns and 3 equations. I can write them down in terms of matrix. Now I can write them down in terms of 1, 0, 0, and 0.25, 0.75, minus 0.433, 0.25, 0.75, 0.433 as a matrix or coefficients, and multiply an array of these unknown epsilon x, epsilon y, gamma xy, and this whole thing gonna equal to a 133 minus 92 minus 319, and that's it. That's it. Okay, then you can do the calculation of this equation, and then jump to the conclusion that now epsilon x equal to 133, epsilon y equal to minus 318, and then gamma xy equal to a minus 262. Okay, okay. So now we have all the strain gauge readings. And we convert all the strain gauge readings to the strains in terms of x and y, okay? But the question is to ask, what is the stress? What is the stress generated from this strain? Okay, now we're going to use the generalized Hooke's law, so generalized Hooke's law to obtain the stress from the strain. Okay, so what are the equations I'm going to use, right? So in this setting, let's take a look at it. We're talking about the shell, right? We're talking about the shell with the pressure vessel, right? And these are strain gauges in a weird fashion. It looks like a cruddy face, but that's what we have, right? So in this pressure vessel here, let's take a look. So we have this stress component, y, or for better known as a hoop stress, theta, and then we have a longitudinal stress. So we look at it and we realize that it is basically a plane stress condition. A plane stress conditions. Okay, and be careful though. I have to say this has to be on the exterior. Okay? Because interior, I do have a pressure to consider. Consider the pressure. All right? So this is a plane stress condition. So now, I know it's plane stress, I can use the equation. Right? Equation is pretty straightforward. So sigma x equal to a E divided by 1 minus nu squared inside the strain epsilon x plus nu epsilon y. And this gives me a 207 gigapascal, so multiplied by 3 megapascal, divided by 1 minus 0.29 squared, multiplied by 133 minus 0.29, multiplied by 318, and don't forget to the power minus 6. Where does power minus 6 come from? Yes, come from the microstrain. All right, come from the microstrain. All right, so now I can directly get my stress in x direction, which is 9.22 megapascal. And to make sure I label right, this is actually x, this is actually y. Okay, that goes along with the local coordinate system. Okay, that goes along with the local coordinate system. All right, so now that is the stress for sigma x. All right, that is the stress for sigma x. So consequently, very straightforward, I can calculate the stress in the y direction. All right, the stress in the y direction equal to E divided by 1 minus nu squared multiplied by epsilon y plus a nu epsilon x. And then this is 207 again to the 10 to the 3 megapascal divided by 1 minus 0.29 squared inside the bracket minus 318 plus a 0.29 multiplied by 133, and don't forget the microstrain, okay? Don't forget the microstrain, okay? So this gives me a minus 63.1 megapascal. 63.1 megapascal. So the shear stress is straightforward, right? Tau xy equal to G shear modulus multiplied by gamma xy equal to A0 220 megapascal. This has become megapascal and 262 to the power of minus 6. And don't forget this is microstrain. And this gives a minus 21 megapascal. Minus 21 megapascal. Okay? And you say, where is this 80,200 coming from, right? Where is this 80,200 coming from? This is actually coming from the shear modulus G, which is the equation of Young's modulus E divided by 2 times 1 plus nu. Okay? So that is actually 207,000 megapascal divided by 1 plus 0.29, which is the Poisson ratio, equal to 80,200 megapascal. Okay, so that is where the G coming from. Okay, all right. So this is step 2. I want to move on to find out the stress in a particular component. Remember? Because here, going all the way back, right? This is the coordinate NT. I'm trying to find the stresses with, right? Here. Okay? We just find out the stress in x and y direction. We're yet to find out the stress in the n and t direction. Okay? So what we do, we have stress in the x and y direction. All right? We have stress in the x, y direction. How do we find the stress in the nt direction? So how do we find conversion between sigma x, y to sigma nt? How do we do that? Right. So we do what? Stress transformation. So third step, stress transformation. Okay. So in this, my sigma n would equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2. Okay. Cosine 2 theta plus tau xy sine 2 theta. Okay. And sigma n would equal to, bring the number in, 9.22 minus 63.1 divided by 2 plus 9.22 plus 63.1 divided by 2. Okay. And this is cosine 2 divided by 250 here. This is the theta n. Okay. Theta n. Okay. I think I have a typo here. Let me just clean that up. Okay. I have a typo here. You see my y is, yes, no, I think I'm right, okay. No, I think I'm right, okay. All right, so carry on. This is 21 sine 2 multiplied by 50 degrees, okay? So I eventually get my stress in n component, that is minus 53.9 megapascal. Okay, so to convert the stress in the t direction, sigma t equal to a sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 cosine 2 theta, so 50 again, minus a tau xy sine 2 theta, so 100 degrees again. And this actually gives me a 0. Okay, and now tau nt, which is the shear stress, equal to a minus sigma x minus sigma y divided by 2 sine 2 theta, so sine 100, plus a tau xy cosine 100, and this gives me a minus 32 megapascal. Okay, all right, so pretty straightforward. I have my n, I have my t, I have my nt. So problem solved. Okay, now the question is, all right, Bob, you just solved the stress transformation, right? So far, I haven't feeling anything about a pressure vessel. I haven't felt anything about a pressure vessel. So what does this to do with a pressure vessel, right? What does this thing to do with a pressure vessel? So this is what we're going to do. I say, let me ask another question. For follow-up, I say if the R equal to a 12-inch, which means the pressure vessel radius 12-inch and the thickness T equal to a 1/4 inch. Okay, I say if the allowable stress in the n direction of the steel is 60 megapascal, what will be the maximum pressure P? Okay, so now let me turn the table around. I say if the radius of the pressure vessel is 12 inches, T is 1/4 inch, and I tell you the allowable stress in n direction is 60 megapascal. What will be the maximum pressure P? Okay, to have a visual image, I want to redraw my figure, right? So this is my pressure vessel. This is the radius R. Okay, I say now if I have the coordinate system set up like this, this is Y, this is X. Okay, my N is here, and theta N here equal to 50 degree. My question is, if I try to limit my stress in n direction, sorry, let me change the color here. If I try to limit the stresses in the n direction right here, has to be smaller than 60 megapascal. Okay, what will be the pressure? So how do we do this? Okay, so this seems quite complicated, right? Seems like quite complicated. But you haven't realized the previous two parts of the problem prepared us for this already. How? This is how, right? You look at this equation right here. What's this about? This basically tells us if I know the stresses in X and Y, and I can find the stresses in, or if I know the limitation on N, I probably can find a relationship between that constraint to the stress in X and Y direction. How so? This is how. Because now, if I say sigma N, let me rewrite it, equal to half of x plus y plus x minus y divided by 2 cosine 2 theta n plus a tau xy sine 2 theta n. If this is equation now, if I know sigma x, sigma y, and tau xy, I can find the limitation on sigma n, isn't it? In this setting, actually, let's take a look. So sigma x is actually equal to our longitudinal stress, isn't it? So that is PR over 2t. Sigma y is actually the hoop stress, and that is equal to a PR t. Right? Double check at the beginning of the class. Longitudinal stress PR over 2t, hoop stress PR over t. Right? So we're good. So these are the stresses actually. How about shear stress, you say? We just said it is 0, right? We just said in the beginning of the class this is 0. Okay? So now we basically already know the stresses x and y. All we need to do is convert to sigma n, find out what is sigma n. So sigma n essentially will equal to a PR over 2t plus a PR over t divided by 2, okay, plus PR over 2t minus PR over t divided by 2 cosine 100 degrees plus a 0. Okay, so now this becomes a PR over t, top here, half, 1, half, plus PR over t, top here, half, minus 1, half, cosine 100 degrees plus 0. Okay, plus 0. Okay, so I want to calculate all this. All I need to do is to find out, right? Find out what is the n. What is n? So I'm going to carry this in. I want to say this basically equal to PR over t. Here, this is 1.5 divided by 2, 0.75, right? 0.75. And then this is minus 0.5 divided by 2, so minus 0.25 cosine 100 degrees. Okay. Okay. So this is equal to a, let me find my calculator. All right, let's see, calculator. Okay. Jump out, say calculator. Calculator. Okay. Okay. All right. Okay. Well, let me stop right here because I have to get going on a part of it, and we will resume